Hello, Chem 201 Organickers. There's another topic that I would like to discuss. It has to do with molecular polarity. Depending on the prerequisite class that you've taken in order to be placed in this class, your understanding of molecular polarity can vary a little bit. So I just want to bring everybody on the same page and sort of start with what you need to know in order to succeed in this class. So let me share my screen. What I want you to know is that we are going to be looking at molecular polarity. So remember, in organic chemistry, we are mostly dealing with covalent bonding. And remember, to form a covalent bond, I'm sharing electrons between atoms. So I have two nuclei. I have this nuclei and I have this nuclei. I have the electron cloud from this atom. I have the electron cloud from this atom. And I'm going to form a bond when the attractions between the nucleus electron and electrons are greater than the repulsions between the nucleus and the electrons. Remember, like charges repel, opposite charges attract. So if I have a positively charged nucleus and then I have negatively charged electrons, right? Those electron clouds are actually going to be trying to repel each other. The nuclei, which are positively charged, are going to be trying to repel each other. But then there's that sort of perfect distance where the nucleus electron attractions are maximized and they become greater than those repulsive forces, which results in an attractive force that binds the atoms together, and I form a covalent bond. We know that there are several different types of covalent bonds. I can have nonpolar and I can have polar bonds. In order to determine if my bond is polar or nonpolar, I need to be able to look at electronegativity of the atoms that are engaging in the bond. Electronegativity is the ability of an atom in a molecule to attract the shared electrons in a covalent bond. So if I have down in this range, I have my electronegativity is going to be 0 to 0.4. That's the difference in the electronegativities between the two atoms that are engaging in the bond. I'm going to have something considered to be nonpolar covalent. Here, when my change in electronegativities, the difference in electronegativities is between 0.5 and about 1.9, I'm going to have polar covalent bonds. And then when I get to my change in electronegativity greater than 2.0 or so, that's where I get my ionic bonds. Now this is sort of a sliding scale. This is a spectrum of bond types. So as I go from here all the way down here, right, I'm increasing the polarity of the bond until I get to fully ionic, where I have a complete transfer of electrons, and it's the electrostatic attraction between those two charged particles that actually give me the bond that's referred to as an ionic bond. So here's an example of something that is pretty much completely nonpolar covalent. If I look at Cl2, right, this is the Cl2 diatomic molecular elements of chlorine, right? I actually have two bonding electrons, which are shown here as dots. They're going to be completely symmetrically distributed between the two chlorine atoms. Those bonding electrons are going to be equally distributed because the difference in electronegativity is equal to 0. This is actually also referred to as pure covalent bonds. If I change the atoms and I still have fairly symmetric distribution, what I'm going to get is a nonpolar covalent bond. So what I really have to look at is my change, my difference in electronegativity between the atoms, and then I can assess whether it's going to be nonpolar, polar covalent, or ionic. But here, if you look at this electrostatic potential map, I have this yellow-green color represents a neutral atom, which indicates that I have this totally the symmetry and where the electrons are distributed between the two nuclei. This is HCl, right? HCl, hydrogen chloride. When it's in water, it forms an acid, which is hydrochloric acid. We know that my electronegativity for hydrogen is going to be much lower. So I have electronegativity of about 2.1 on the hydrogen. My electronegativity is, let's see, maybe 3.5, something like that, 3.0, 3.5. I'd have to look at a chart to be sure. But what I know is, and you can see with this electrostatic potential map, this area of the molecule, the Cl, has an increase of electron density, right? Those electrons are sort of being pulled over to that side, which means this is going to become positively or partially negatively charged, and this is going to become partially positive, right? Because this is lower electron density. If I shift my electron charge, my negative charge to the chlorine, there's going to be a higher amount of a negative charge around the chlorine and a lesser amount of like negative charge around the hydrogen. So the hydrogen part of the molecule becomes partially positive because it's losing electron density. And the part of the molecule that has the chlorine becomes partially negative because it's gaining electron density. And that happens because the electronegativity of chlorine is much higher than the electronegativity of hydrogen. So this is going to be considered a polar covalent bond. Now, if I look at sodium chloride, this is ionic. So my sodium is a metal, my chlorine is a nonmetal. They're spaced very far away from each other on the periodic table. The difference in electronegativity is going to be greater than 2. So what I have here is an ionic bond. So I have full transfer of electrons in this case. And what I have is my sodium becomes fully positive, my chlorine becomes fully negative. You can see by this red color that this is definitely negative. This totally blue color means that is definitely positive. So this is going to be my sodium, and this is going to be my chlorine. And you're going to have those charges because they've actually transferred electrons. So that's bond polarity. If I want to decide if a bond is nonpolar or polar or ionic, I'm going to look at the two elements that are engaged in the bond. I'm going to figure out the difference in electronegativity. If it's between 0 and 0.4, it's going to be nonpolar covalent. Between about 0.5 and 1.9, it will be polar covalent. And any electronegativity difference greater than 2 would be considered ionic. There are exceptions that we'll talk about because those exceptions actually occur in organic chemistry for the most part. But right now, we just want to lay the foundation. So how can I translate this into something else that I always have to consider, which is what is the overall polarity of the molecule itself. So not just the atoms that are engaged in the bonds, but does my molecule have an unequal charge distribution among the electrons, which means that one area becomes more partially negative and another area becomes more partially positive. To do this, I have to use VESPER. I have to figure out the molecular geometry. I have to consider what my bonding is. Do I have polar bonds in the molecule? If I do, what is the orientation of one polar bond to another polar bond in the molecule? And then I have to figure out, does this create an internal charge distribution within the whole molecule, not just within the bonds? And to do that, I have to figure out the geometry of my particular molecule. So we learned this before in VESPER, right? You have to be able to assess these, use 2 electron groups, 3 electron groups, and 4 electron groups to figure out what my electron geometry and my molecular geometry is. And then I'm going to look internally and look at each individual bond and see that how it affects the electron distribution in the overall molecule. So just for an example, we just talked about HCl. This is a dipole arrow, and it's indicative of something called the dipole moment. This is always the positive charge, and it's pointing to where the negative higher electron density is. So remember, this is partial positive and this is partial negative. The chlorine is pulling those electrons towards it, which means this is electron deficient, this is electron rich. And when I look at that electrostatic potential, one side, the side by the hydrogen, has lowest electron density. It lost some negative charge because those electrons were pulled to the chlorine. It's partially positive, whereas the chlorine, because it's pulling those electrons to it, is becoming partially negative. This molecule is linear, right? So I just have the shift of the electrons in one direction. There's really only 2 atoms, so the bond polarity in this case is actually the molecular polarity. So the HCl bond is polar. The net result is I get a polar molecule because there's nothing that cancels that out. I have a permanent dipole where the chlorine part of the molecule is partially negative and the hydrogen part of the molecule is partially positive. Now this is pretty simple when I have a situation where there's just 2 atoms in the molecule, but that's definitely not always the case. In fact, that's very uncommon. So let's look at carbon dioxide. Right here, I have a central atom, carbon, and then I have 2 oxygen bonds to the carbon. So I have a carbon-oxygen double bond pointing to the right, and I have a carbon-oxygen double bond pointing to the left, right? This is going to be linear because I have 2 charge clouds, right? And this part is going to be partially negative. This is partially positive. This is partially negative. This is partial positive because the CO bond itself is polar. If you look at the difference in electronegativity, that falls within the polar covalent range. So this is a polar covalent bond. Here's the problem. I have electron density shifting to this direction. I also have electron density shifting to that direction. Because those 2 bonds are equal in their difference in electronegativity, they actually cancel out. And what I get is a net 0 dipole because this molecule actually happens to be nonpolar as a molecule. So here, it contains 2 polar bonds. It contains 2 carbon-oxygen bonds, but because the dipoles are equal and opposite, they cancel out, so what I get is a 0 dipole. So this is actually a non-polar molecule that has polar bonds. So what we're seeing is it's not sufficient just to have polar bonds in a molecule and say it's polar. I have to look at the effect internally on the entire molecule, all of the atoms. And to do that, I'm going to use an approach where I have to track all the dipoles in my particular molecule. Here's another example. When I look at water, water is actually bent. Don't forget I have those 2 electron pairs there. So the electron geometry is tetrahedral. The molecular geometry is going to be bent. Hydrogen oxygen is a polar covalent bond. But because of this bent geometry, I have electron density sort of pointing up in this direction and more in this. Well, if I think about it, what I actually end up with is sort of a resultant that goes up the center. This is very partially negative. In between these 2 hydrogens is very partially positive. So this, because of its bent geometry, I have 2 equal dipoles. The H and the O are equivalent to each other, but they're pointing in such a way where one is going this way and one is going this way. Those dipoles do not cancel. So it's not linear, it's bent. So this is going to be a polar molecule as well. So the conditions for polarity in terms of the overall molecule is it has to contain polar bonds, right? So I have to have a covalent bonds that have a specific difference in electronegativity that falls within the polar bonding area. But I also have to have non-uniform distribution of polar bonds. So I have to ask myself, do my dipoles cancel out? If it's no, it'll be polar. If it's yes, it'll be non-polar. So you have to get pretty good at sort of reading these dipoles. If you've ever had vector addition, which you don't have to have had, many of you, most of you have not looked at vectors. But if you look at this, you can think of these vectors as being a dipole. If I have a dipole that goes to the right, and then I have another dipole that goes to the right, what I'm going to get is a resultant that actually is the sum of the 2 dipoles. So if I have A and B and consider those being dipoles, the resultant, the resultant vector, the resultant dipole is going to be a sum of those. Since they're both in the same direction, it's just additive. Now look at example 2. I have something that's much greater to the right and lesser to the left. So this part is actually going to subtract from that overall dipole. And my resultant is actually, when I sum them up, less than B, but greater than A. So this is how I'm going to look at my dipole. I have to look at them and try to figure out if they cancel or if my density is actually pointing in one direction or another. Here's an example like CO2. Those cancel, so my resultant is 0. This would be a condition where I would be nonpolar. This would be polar, and then this would be polar if I look at my vectors. Same thing here. A lot of times I don't have things that in my geometries, I don't have any geometry that just is simply a straight line. So here, if I'm going this way and this way, this is where my resultant is. So this would be polar. This is also polar. In fact, all of these examples would be polar except for this one. Here is a special case where I have three things. This is sort of like my trigonal planar. If all of my bonded atoms are equivalent, I have symmetry, and what I get is 0, which would be nonpolar. So to put it simply, in terms of chemistry, I am going to look at the molecular geometry. We've learned about these. I can have a linear geometry, bent, trigonal planar, tetrahedral, trigonal pyramidal. This chart gives you an idea. If I have linear and the dipole moments are where I have two identical polar bonds that point in opposite directions, the molecule would be nonpolar. But I have to have two identical polar bonds. So this is my carbon dioxide here. If I had carbon and I replaced one of the oxygens with the sulfur, right? This is about the same electronegativity. So this would end up pointing in this direction, which would be polar, because the electronegativity of oxygen is much greater than the electronegativity of sulfur. So that would be where I have something like this, and then maybe a little bit there, right? But the net result is I'm still pointing to the right. Bent, if I have the dipole moments of two polar bonds and my angle is less than 180 degrees, where it's not linear, they're not going to cancel. And basically, I have polar molecules when I have a bent geometry with a polar bond. This is trigonal planar. So this is going to be sort of my, if I have boron trifluoride, I have symmetry here. These are all going to be polar bonds because boron is much less electronegative than fluorine. But because of the geometry, if I have this, my bonds, dipoles are going to cancel. So I end up with non-polarity. So again, if I have something like this, where I have two fluorines and a hydrogen, right? This is going to be pointing this way. This is going to be pointing this way. This one is much less. So I'm probably going to have a net result in this direction, which is going to give me something that is polar. So I have to look at the symmetry of the bonds as well as the geometry. Tetrahedral. If all of these bonds, right, if this atom, this atom, this atom, and this atom are identical, if I have tetrahedral, that will be a nonpolar because all the bonds will cancel out. If I have something that's different, so for example, if I have something here now that's different, right? If I have the orange, I'm going to have a polar because now I'm sort of going up this way and I don't have symmetry. It actually depends on the electronegativities of the atoms in the geometry, but I'm sort of looking at carbon being the central atom and then other atoms doing other things. But you have to follow the dipoles, figure out where you have electron density and where you don't, and then you can go ahead and make an assessment on if those dipoles cancel or not. If they don't cancel, chances are it's going to be a polar molecule. If they do cancel, chances are, well, it's going to be nonpolar. Trigonal pyramidal, right? If I have this three polar bonds and it's trigonal pyramidal, they're not going to cancel this is going to be a polar situation. Again, if I look at nitrogen, right, what I'm going to have is sort of these bonds coming up this way because this is more electronegative. So instead of having it go down here, because of the difference in electronegativity, what I have is sort of a resultant that goes up this way in ammonia. But here, this resultant is just showing you what happens if this is less electronegative than these atoms out here. Here, nitrogen is more electronegative, so my dipoles are in the reverse direction. But basically, in all cases in which the dipoles of 2 or more polar bonds cancel, the bonds are assumed to be identical. If one or more of the bonds are different from the other, the dipoles will not cancel and the molecule will be polar. So this is a huge piece down here that you have to apply when you go through and assess whether a molecule is polar or not polar. So to do this, you need to draw the Lewis structure. You need to determine the molecular geometry. You have to look at electronegativity and figure out whether the bonds in the molecule are polar. If there are no polar bonds, the molecule is nonpolar. And then when there are polar bonds, you want to look and see if they add together, if all the dipoles add together to give a net dipole moment. If everything cancels out, it's going to be nonpolar. So let's look at formaldehyde, right? We've looked at this in Lewis structures before. What I get is this, right? So when I look at this, I have my electron geometry has 3 charge clouds as trigonal planar. My molecular geometry is also trigonal planar. My carbon-hydrogen bonds, if I look at the difference in electronegativity, that falls in the nonpolar range. If I look at my carbon-oxygen bond and I look at the difference in electronegativity, that is a polar bond. So basically, I have a polar bond, right? This is going to point up this way. Oxygen electronegativity is greater than carbon electronegativity. So this part is going to be partial negative. This is going to be partial positive. Whereas this is kind of going to just be there. So what I have in this case is I have this net dipole. So I do have a net dipole. So therefore, this molecule is polar. And this would be considered to be a permanent dipole, which is going to be important when we look at when we look at intermolecular forces. Now, it's really interesting to know how polarity affects physical properties. We're going to spend a lot of time on that in organic chemistry. One of the things I want to mention really quickly in this little review is that molecular polarity affects all kinds of physical properties: melting point, boiling point, vapor pressure. It also affects solubility. So in solubility, we have this phrase, like dissolves like. So polar molecules are attracted to other polar molecules, and therefore like polar dissolves like polar. Polar substances tend to be soluble in other polar substances. Nonpolar substances also tend to be soluble in other nonpolar substances. We know that water is polar, we've talked about this. So other polar substances will dissolve in water, also ionic compounds, but you have to remember you have solubility rules that sometimes just because it's ionic doesn't mean it's automatically soluble, because it's actually going into solution is much more complicated, but we don't have to worry about that. Also remember that some molecules have both polar and nonpolar parts, and this you have to look at as case by case. If the polar part is larger and more important in the overall structure, the overall molecule will probably be polar. If the nonpolar piece is really large compared to the polar part, sometimes that will determine physical properties as well. So we're going to learn a lot about this in our course, but this just gives you sort of an overview. This is sort of how you can use this to assess physical properties. Oil is a hydrocarbon, and typically it only has multiple carbon and then hydrogen bonds. And we'll talk more about those structures when we get into this. This would be an alkane. It only has carbon-carbon bonds and carbon-hydrogen bonds. These bonds are nonpolar. So oil is a nonpolar substance. We know water is polar, and you can see here that they separate out. And that's because the nonpolar substance is not going to dissolve in the unlike polar substance. Like dissolves like. Polar dissolves polar, nonpolar dissolves nonpolar. I can't really get something that's nonpolar to dissolve in something that's polar and vice versa. So again, we'll be talking about that more, but this is sort of your introduction into molecular polarity. See ya.